Hello, Algebra Scholars! Today we're going to be discussing inverse functions. Before we begin, as per usual, please make sure you have your notes or at least a blank sheet of paper to write on, something to write with, and a calculator may be handy for this unit. So let's get into this idea of an inverse function. Now before we jump into this new topic of an inverse, I want to take a minute to quickly discuss what we discussed with the one-to-one functions. We discussed that a one-to-one function was a function in which the y values did not repeat. But we really didn't say why this was important. Why do we care about one-to-one functions? Well, if a function is one-to-one, what we can say is that that function's inverse will also be a function. In general, any function should have an inverse, but not every function's inverse will also be a function. Now, what does it mean to be an inverse? Well, an inverse is something that cancels it out. It undoes it. Think opposite operations. Addition and subtraction are opposite operations. Things like the square root of x and x squared are opposite. They cancel each other out. These are examples of inverse functions. Now, some other properties that go along with our inverses. If we look at the x and y values of a function, its domain, the x, and the range, the y's. When we find the inverse, those values are interchanged. They're flip-flopped. All of the x values for a function will be the y values for its inverse. All of the y values for a function will be the x values for its inverse. Another property of inverses and their functions are that their graphs are reflections across the line y equals x. So the line y equals x is this diagonal line that goes through the first and third quadrants. If you think about putting a mirror on this line, or perhaps folding your graph across this line, your two graphs should in fact be mirror images. So if I had something like this on one side, the mirror image on the other side should look something like this. So these two graphs should be inverses because they are reflected across that line. Now, the last important thing to consider in our definition is the notation. When you see an f with a little -1 exponent, this tells us we have an inverse function. This is read f inverse of x. Now, I do caution you, you need to be careful with this notation. This little -1 isn't actually an exponent. This notation tells us we have an inverse. Recall that an exponent of -1 tells us we're going to flip the fraction. So x to the negative first power is actually 1 over x. This is not a negative first power. This is an inverse. So you really have to be careful with the context of where you see this notation. Is that -1 with a variable or perhaps with a number? If that's the case, then we have an exponent telling you to flip the fraction. If you see that -1 in the function notation, f of x or perhaps g of x, then you know that it is an inverse and not an exponent. So do be careful. Make sure you're looking at the context of whether you have an inverse or an exponent. So let's get into some problems dealing with these inverses. The first thing we're going to look at is whether or not we have two functions that are inverses. We have something called a two-sided inverse test, and this is going to use the idea of composition of functions. If you plug an inverse into a function, it should cancel everything out so that x is all that's left. As well, if you plug a function into its inverse, again, everything should cancel so that all that's left is x. So let's look at a couple of examples to try this test and see how it works. Here we've got f of x and g of x. We want to know whether or not these two functions are in fact inverses. So I'm going to take the f of x function and the g of x function and create a composition of functions. I'm going to first plug g into the f of x function and see if everything cancels. Now, looking at the two functions before we actually plug in, it seems like these two are excellent candidates for inverses. We've got a -8 and a +8. That should cancel each other out, right? We've got a times 6 and a 1 divided by 6. Multiplication and division are opposites. They should cancel each other out. So this probably will work, but we need the test to be certain. So let's give it a try. If I plug g into f, that tells me everywhere in the f function that I see an x, I'm going to change it into this g of x function. So instead of 6 times x, I'm going to have 6 times the g of x function. So now I'm going to have 6 times that entire g of x function of 1 over 6x plus 8. And then I'll subtract the remaining 8 that was in the f of x function. All right, let's simplify. Let's see where this takes us. Distributing the 6, I know 6 times 1/6 simplifies to just 1, so 1x. 6 times 8 will get 48. And then we'll bring down the minus 8 from the previous line. Continuing on, I find that we get an x plus 40. Now this does not pass our test. We should have just gotten x all by itself at the end. So since we've got x plus something else, these are not inverses. We must isolate x, get it by itself completely with everything else canceling. Since the 40 didn't have anything to cancel with, these are not inverses. Let's try another one. Again, I'm going to create a composition of functions. I'm going to start by plugging the g of x function into the f of x function. I want to know, does f of g of x cancel everything except the x value? So let's try it. We've got x cubed. So instead of an x cubed, I'm going to take the g of x function, that entire value, and cube it. So my g of x function I know is the cube root of x minus 4. So I will plug that in, bring everything else down, and simplify. All right, a cube root and a cubed exponent. Cube root to the 3rd power, those two things cancel, and that leaves us with just the numbers inside, x minus 4. I'll bring down the plus 4 from the previous line, and it looks like, yes, the 4's will cancel, leaving us with just an x. So we've passed the first part of our test. F of f inverse of x does equal x. But we're not quite done. We need to make sure the second half of the test also works. There are occasionally cases where this will work, but this will not. So we do need to test both sides. So now let's try this again, but instead of f of g of x, we're going to replace it with g of f of x. So we're going to plug the f function into the g function. So the g of x function was the cube root of x minus 4. Everywhere we see an x in this function, we're going to replace it with f of x. So f of x we know is x cubed plus 4. Everything else from the g of x function will carry down as is. All right, so now let's start simplifying. We've got a plus 4 and a minus 4. Those are going to cancel, leaving us with the cube root of x cubed. Once again, we know a cube root and a cubed exponent will cancel, leaving us with just x. So this tells us that since f of g of x and g of f of x both worked out so that everything canceled except x, we do in fact have inverses. That's our two-sided test. Now that we know how to test for inverses, let's see how to find inverses. Maybe we don't have two functions, we only have one, and we want to know what its inverse is. We have a short 4-step process that we can go through to find the inverse. So let's take a look at this one. We've got f of x equals a negative 1/2 x plus 2. Step 1 says that we're going to replace the f of x value with a y. So we're going to say y equals a negative 1/2 x plus 2. Step 2 says to interchange the x and the y values. Recall from our definition of a function that the x and y values, the domain and range values, are in fact interchanged. So it makes sense that to find our inverse, we need to switch those values. So the x moves to the y place, and the y moves to the x place. Once we've switched the values, step 3 says to solve for this new y value. I want to get y by itself. So let's subtract the 2. Let's multiply by 2. Rather, let's multiply both sides by a negative 2 to get rid of the negative 1/2. Finally, step 4 says that we're going to replace y with f inverse of x so that we use our proper notation. So f inverse of x should be a negative 2x plus 4. The next thing asks us to take a look at the graphs and make sure that we've done things correctly. So I'm going to graph both my original function and its inverse and make sure that these are in fact inverses, that I have not made any mistakes. So I'm going to start with a negative 1/2 x plus 2. Then I'm going to graph my negative 2x plus 4. When I look at my graphs, they should be reflections across the line y equals x. So there's my first function, f of x. And here's my inverse function, f inverse of x. Now, to really tell if these are inverses, our graph is a little distorted right now, and I'm not sure exactly where that diagonal line goes. So I'm going to go back to y equals one more time, and I'm going to put in the line y equals x to make sure that everything looks okay. I'm going to make it a dotted line so I know where it is. And I'm going to put in y equals x. I'm also going to change the zoom. I'm going to change this to a square window. Having the window squared instead of slightly pulled out as it is now is going to make it a little easier to see if we actually have a good reflection. So I'm going to change it to zoom 5. This should make it a little bit easier for us to see the reflection. So there's f of x. Here comes f inverse of x. And lastly, we should have that diagonal line. So now I think it's a lot easier to see that these are in fact reflections. If I think about putting a mirror right on this diagonal line, these images should match up. This piece on the inverse function should match up with this piece on the function. This piece on the inverse function should match up with this piece on the function. Folks, I'd like you to take a minute and try number 14. Use your steps to create the inverse. Replace the f of x with the y value. Switch the x and y values. Solve for y, and then replace the y value with the inverse notation. Check your work by looking at the calculator. Do the functions actually look like inverses? Give it a try, pause the video, see what you come up with. Alright folks, now that you've had a moment to try it, let's see how you did. We're going to say y equals, instead of f of x equals, the square root of x plus 3. I'm going to switch my x and y values. X becomes y becomes x. And now I will solve for y. I'll start by squaring both sides of my equation to get rid of the radical. Then I will subtract the 3. So this gives me my new function. F inverse of x is equal to x squared minus 3. So now, looking at our graphs, let's plug these in and see how we did. The function, square root of x plus 3. The inverse, x squared minus 3. And let's look at our graphs. There's the function. And here's the inverse. Now this looks a little bit funny because our inverse has 2 pieces, where our function only had 1. This still works out as an inverse. However, if we went backwards and found the inverse for this one, we would not find that its inverse would be a function. So this is why that one-to-one test was important. This red graph, its inverse is not a function. For the red graph to have a full inverse, we would also need the other half of this piece here. So for the original blue piece to have an inverse, we actually only need half of this graph. In other words, if we just look at the red piece from here over, this is enough to get our inverse. So this inverse actually gives us a little bit of extra, which is okay, but it would not be okay going in the other direction. Remember that if this function does not pass the horizontal line test, its inverse will not be a function. So the red graph's inverse is not a function, but the blue graph's inverse is. So that is one of the kind of tricky parts about finding these inverse functions. As far as this problem goes though, guys, this is okay. The direction we've gone is correct. But again, if we tried to go backwards, we would not have a full function for this inverse. So these inverse functions are kind of a one-way street. Okay. Now, one more thing to check with our graphing calculators. I do want to go back to this problem number 11 and 12. You can also verify these using your graph as well. We did this two-sided test, but we didn't look at the graphs. Another quick way to see if these are in fact inverses, or at least to check your algebra, would be to look at the graph. So if I key in this 6x minus 8, and I key in this 1/6 x plus 8, it should be pretty easy to see that these are not inverse functions. We'll have a good example of why these are not inverses because they won't be reflected across our line. So here's the original f of x, here's g of x, and here's the line over which they should be reflected. So here's a quick example showing you of two functions that are not inverses on the graph. All right, guys, that takes care of our work for today on inverse functions.